Thank you, everyone, for joining us today. I am thrilled to have you here. I'm excited to introduce you to Meredith Kelly. She is a professor and chair of the Department of Earth Sciences at Dartmouth College. Meredith is a climate scientist whose research focuses on glaciers, ice sheets, and lake sediments to better understand how and why climate has changed over time. She also serves as the faculty director of the Dartmouth Climate Collaborative, which is a new college-wide initiative that connects and strengthens Dartmouth's work on climate and long-term resilience. Meredith earned her Master's of Science from the University of Maine and her PhD from the University of Bern in Switzerland. She's been a faculty member at Dartmouth for nearly 17 years, and she was brought to our attention by a Hanover resident who came across her work. And we are so glad that they shared it with us. Please join me in welcoming Meredith Kelly.
And her parents are my neighbors here at Kent, Marty and Dennis.
Wonderful. Thank you, Meredith.
Thank you so much. And thank you for inviting me and for having me here. And unfortunately, my parents are in Hawaii right now, so it's probably very early in the morning for them. Great. Okay. Okay, so let me look at the time and just check in with you, Jenna. You want this to be about a half an hour or so?
That would be great, so we have room for some Q&A at the end.
So I can, of course, after being a professor for 17 years, I can talk a lot. So I will try to get to the point, and I hope this is interesting. And what I'd like to present is about my work as a scientist on glaciers and climate change. And then I'd also like to give you an update about what we're doing at Dartmouth. And I'll start with the science work. Is my sound okay? Everybody can hear me, okay. So, and can you see my cursor when I move this around? Okay, that's great. So I'll just acknowledge to start with it, you know, I'm indebted to Dartmouth for the support over the years, and also the National Science Foundation and another wonderful organization called the Comer Foundation, which is a family foundation that supports climate change research. And so let me also acknowledge a huge team of people, all of whom are younger than me. And these are the students who've been involved in this over the years. So I've had a number of undergraduates involved, a number of PhD and master's students, and it's really been a super fun experience getting to have this role and getting to ask big science questions, but then also help train the next generation. I also have collaborators in the US and around the world, so I'm going to mention some of the international work that I do, and all of this is done in collaboration with folks at universities in the countries where I'm working. So let me see if the little bar up here is in my way, and I don't know if it's in your way. So let me see if I can hide this for a second. Hide, loading, meeting. There we go. Is that better? At least better for me. Okay. So I am a climate scientist, and I use the record that's preserved in Earth's history to help us understand better our climate system, with the goal of trying to be able to better predict where we're going, right? In this time where we're basically running a science experiment with our climate, of pouring lots of greenhouse gases in and not knowing what's going to happen. So the time where I really like to focus my work is this period called the Quaternary period. That's the last 2.5 million years of Earth history. And the reason I like to focus on that period is because in general, Earth looked very similar to what it does today. And that means the continents were in the places where they are now, and ocean circulation and atmospheric circulation generally functioned as it does now. So the Quaternary is a good model for how our climate system works today, and serves as sort of that basis to study. The other really interesting thing about the Quaternary is that there has been this, it's been a time of climate change and climate fluctuations. You all know this, of course. These are the glacial interglacial cycles. Those are times when large ice sheets grew in the Northern Hemisphere and then shrank. Multiple times. There have actually been 25 glacial interglacial cycles during the Quaternary, so about every 100,000 years we make that switch. And this gives us an example of how our climate system undergoes rapid changes. And understanding this can help us understand how these systems work and how they may change in the future. So this is an interesting diagram. It's a record from an ocean sediments, so deep ocean sediments that have been cored. And we can tell something about both ocean temperature and ice volume. And basically, time is on the x-axis here. You can see 5 million years ago until now. 5 million years ago, it was relatively warm and there was no ice on the planet. And then about just after 3 million years ago, temperature decreased and we started getting into these fluctuations where it was starting to be warm and then cold and then warm and then cold. And these are the glacial interglacial cycles that I'm talking about. And you can see those sort of intensify in the last million years. Okay. So we have an idea of what caused these. And I'm going to chat about that and then maybe suggest that we don't fully understand these. So let me go to my next slide. Oops, let me see how I do this. There we go. Okay, so you probably also heard of this, that these glacial interglacial cycles can be explained by something called Milankovitch theory. So Milankovitch was a Serbian mathematician who back in the mid-20th century came up with this idea that small changes in Earth's orbit influence the amount of incoming solar radiation at high northern latitudes, and that allows these northern large ice sheets to grow and then forces them to shrink. And these changes are things like the tilt of Earth's rotational axis, the relative elliptical shape of Earth's orbit around the sun, and something called sort of the wobble of which way Earth's axis is tilted, driving when we have summers versus winters in the Northern Hemisphere and what position that is in Earth's orbit around the sun. So what's interesting about these changes is that they happen very slowly. So these changes from the wobble up here on the top panel to the shape of Earth's orbit around the sun in the lower panel generally range from periodicities of about 20,000 to about 100 or even 400,000 years. So they align with the timing of glacial interglacial cycles, and in general can explain some of that, but they don't explain all of it. And I want to point out one part that they don't explain, and that's actually the ends of these ice age cycles, which I'm going to start to refer to as terminations. Termination being the end of the cycle. So bear with me, I know these are wiggly lines. If we look at the bottom panel, again, the x-axis is time, and now I'm showing the last about 500,000 years or 500,000 years ago till now. And what you see, this is that same ocean sediment record, and you can see that cold is down here. So this is a glacial period, and warm is up. This is where we are now, the current interglacial. You can see there's sort of this slow slide into cold temperatures, large ice sheets, and then at the end of that, there's this really rapid end of an ice age. And then another slow slide into another glacial period and a rapid end of the last ice age. So the most rapid end of the last ice age was about 20,000 years ago. That's here, the last termination. And while Milankovitch can explain the sort of this slow slide into the glacial periods, Milankovitch can't explain that rapid end of the last ice age. So that's the big question that I've been working on and mulling over is why? And if it's not Milankovitch, then what other Earth systems are causing that really rapid change? And if we understand that, can that help us understand if we're experiencing a rapid change in the future, how these systems might behave. Okay, so let me get to what I do, and then I'll give you a few insights as to what we've learned. So I look at glaciers to understand, help us understand these changes. Glaciers aren't the only way to do this. As I mentioned, people look at ocean sediments too. I look at glaciers, and I love glaciers because they're amazing and beautiful, but they're also really, really sensitive to climate. And you all know this, right? We can look around the world today and see that glaciers around the world are shrinking because of global warming, because of the rise of temperature. This is an example of this and how sensitive these actually are. So this is Jakobshavn Glacier on the west coast of Greenland. And this is a view out of an airplane looking down at the Greenland ice sheet. And this is Jakobshavn flowing out into the ocean here. This is that same view, but from satellite image. So the edge of the Greenland ice sheet and then Jakobshavn out into the ocean. And the lines here mark where the edge of that glacier was over the past about now 170 years. So this outermost line is 1850 AD. And the innermost line, so sorry, this is an older figure, is about 2010. The black lines show historical records of where the ice margin was, and the colored lines are satellite imagery. So we can really track super well how glaciers around the world are responding to temperature. And this is tracking temperature rise since the 1850 is now at about 1.5 degrees C global average. So this is a really rapid response. So I like to use this and say, well, okay, let's think about why this happens, and then let's see if we can apply it. So glaciers are this cool system that's sort of like a bank account, right? They exist in areas where that's cold, that receives snow. That snow accumulates if it doesn't melt and turns to ice, generally flows downhill into an area that's a little bit lower elevation and warmer, or into the ocean where it ablates or loses ice, loses mass. And it's a pretty simple situation, right? If you put in more snow, if you put in more money into the bank account, your bank account grows. If you start melting the ice, take money out of that bank account, it's going to shrink. The sort of dividing line between the input and the output in this system is what I refer to as a glacial snow line. And when we look at this around the world, this often intersects the freezing line in the atmosphere. And this gives us a really cool direct connection to climate that we can track. And so that's sort of where I take off here and say, okay, well, that's pretty cool because glaciers exist around the world, right? They're glaciers. This is something called the Randolph Glacier inventory of something on the order of 300,000 glaciers that exist around the world today. In the past, during glacial periods, these were obviously more. But because they're around the world, we can use this, what I'll call proxy or substitute for temperature at a time when we didn't have thermometers on the planet, to look at how temperatures changed and do this in a really apples to apples way around the world. How do we do this? And this is where things get really fun for me, is by looking at these incredible glacial environments and using a tool that I'm an expert in called glacial geology. So glacial geology is the record of what glaciers leave on the landscape over time. This is a mountain in the Wrangell-St. Elias Range in Alaska, and you can see there are modern glaciers there today that flow down to the slope. They end in a little lake here. And when those glaciers end, they, in addition to melting ice, they spit out a lot of sediment. And that sediment over time can form what I call a glacial moraine, which is basically like a ridge of really poorly sorted sediment that marks the glacier margin. And so you can see this modern moraine that has more recently formed. And then you can see outside of that, there's this beautiful other ridge that's vegetated. So that was that's a moraine that marks the glacier extent from a prior time. And that's how we can really reconstruct glacier extents. And through that, use that inference of the glacial snow line to tell temperature. So there are a couple ways, things that I want to know in order to do this. These are my questions here. So what was a glacier extent? How old is that moraine? And what does this tell us about climate? So I'll walk through those three things and then I'll get to sort of what we've learned. The first way to do this is like part of the reason why I love this is because you actually have to go to these sites and look around and walk around and make observations and make maps, which is to me really fun. These sites look like this. This is a moraine on the ground in Colombia, in the Colombian Andes, covered with boulders, quite old. So we're at this site here on the border of Colombia and Venezuela. And then we can also use satellite imagery. And with that, we put together what you see on the right, which is a map of what these moraines look like and make inferences about, you know, what the pattern of glacier flow was and the timing of these. To get at the timing, I also am a geochemist, and I run a chemical lab where we can do dating. So we want to know when this moraine was deposited so we can compare it with glacier records from around the world, as well as other records like records of greenhouse gases or records of ocean temperature. So I do this cool thing called cosmogenic nuclide dating, which is a mouthful. And when I did my dissertation in Bern, I learned how to say this in German, which is even more of a mouthful. But it's based on the idea that our Earth is constantly being bombarded by cosmic rays, which are high energy protons that emanate from supernova in the galaxy. And those particles, those high energy particles, come into the atmosphere. They interact with molecules in the atmosphere and produce what are called cosmogenic nuclides in the atmosphere. That's, if you know radiocarbon dating, that's how radiocarbon is produced. Well, they also interact with molecules in the solid Earth and produce cosmogenic nuclides in the solid Earth. And those can accumulate in rocks over time. So the one that I use is beryllium-10, and that accumulates by the spallation of oxygen-16, which is occurs in the mineral quartz, which is a great common mineral you can find around the world. And I can take a sample from a moraine, take it back to my lab down the hallway here, extract beryllium, send it to actually a really big fancy instrument to get it measured because it's very small quantities, and determine an age of that moraine. So then I can start comparing it with other records. Lastly, we want to know climate. And this is where I call on colleagues who have more expertise in modeling than I do, but I work with some great folks at University of Maine who run computer models, and we can simulate what glaciers look like. So let me start this out. I'll run this and you can see what this looks like. This is a site in Costa Rica that's not currently glaciated, but had glaciers in the past. And what we do is we take a digital elevation model, that's the gray background. And then on top of that, we can place like a two-dimensional ice flow model, and we can start to turn the dials on that. We start with modern climate. And at this site with modern climate, we don't grow ice at all. But if we turn down the temperature, in this case to almost 9 degrees colder than present, we can start to grow ice. And we want to grow ice to the place where we've mapped and dated moraines. Those are these two stars. And you can see this is, I'm showing you a successful run. Some of these runs aren't successful, and that's how we sort of eliminate what climate conditions work and what don't. And from that, we can get at the climate. And so from this site, we can say that, you know, there's no unique answer to this because there are a couple different variables like temperature, change in temperature, change in precipitation, and also something called the lapse rate, which is how fast the atmosphere cools, how much the atmosphere cools as you go up in elevation. But we can start to get climate conditions from this. All right, let me see where I am. Oh, we're good on time. Okay, so I'm a little bit of a different person. Most people who work on glaciers work at, you know, in places that are like sort of naturally cold, and I work in the tropics, which is weird. But there are glaciers in the tropics today, and there certainly were in the past. Again, with this lapse rate, it means you have to go high up in the atmosphere. And the reason I work in the tropics is because the tropics are far away from that Milankovitch forcing, which is at high northern latitude, and they're also far away from the like direct refrigeration effects of the ice sheets. And so we can really see how temperature on Earth is changing by tracking glaciers in these locations that may be more sensitive to things like greenhouse gases rather than Milankovitch or ice sheets. Okay, so let me take you, actually, let me go back. So I'm going to take you here. This is to East Africa, one of the sites where I've worked for over a decade. This is an incredible site in the Rwenzori Mountains of Uganda. Again, it is at high elevation, and we're at 5,000 meters here. There are 3 currently glaciated peaks. This is Mount Speke, Mount Baker, and Mount Stanley. And in the past, it's a really interesting environment to be in because there's this incredible like tropical alpine vegetation that's very different and looks very like warm. But then when you take a look at these environments, you see things here like this beautiful U-shaped glacially carved valley or polished bedrock everywhere, or a lake that's been carved by a glacier. And in fact, we can also find moraines here from those glaciers. They look really different from moraines in Alaska. So if you look at this picture, you can see there's a ridge, there's a line of trees right here, and there's a line of trees right here, and those mark a glacier that flowed from the left to the right and ended in this valley. So these are the features that we look at, and we do all those methods that I just talked about, the mapping, the dating, and the modeling. Okay, let me wrap this up, and then I'm going to get to the Climate Collaborative. So two big takeaways that we've learned, and this is a big figure to show you from one of our papers, that it probably doesn't make a lot of sense looking at first view. So let me again show you that time is on the x-axis here, and this is now 32,000 years ago to 16,000 years ago. So essentially about end of the last glacial period. I'm looking at that termination. And I'm showing Milankovitch forcing, which is for northern hemispheres, this blue line, relatively cold time and then a warm time. Sea level, which is reflective of the large ice sheets being low and then starting to come back up at the end of the last ice age. Greenhouse gases, with all of the greenhouse gases we can measure put together in the solid line and just carbon dioxide with the dots. And this is our data. So this is 5 moraines that have been dated that mark the outermost position of the ice in Uganda, in the Rwenzori, during this time. So these are showing us that the glacier reached a maximum during that sort of maximum glacial period, coinciding with maximum cooling from Milankovitch and large ice sheets. And this moraine here, the timing of this is actually this moraine's up valley. So it's showing us that this red band shows us when warming starts in the Rwenzori. So what have we learned? We've learned that glaciers in the tropics are responding generally to this Milankovitch forcing, and potentially also a low in greenhouse gases. And that's interesting, and we can use this actually to tell how much cooling happened with the amount of greenhouse gas drop at that time, which helps us to understand Earth's sensitivity to greenhouse gases. So there's an agreement with Milankovitch here, but there's a problem that arises in that the warming in the Rwenzori and a couple other sites where I'm working starts early. And by early, I mean it starts sort of at like 20,000 to 19,000 years ago, glaciers start retreating. And it's problematic because the main forcing of warming in the tropics is greenhouse gases, but we don't see those rise until later. So there's a question here. And there's something else that might be driving that warming in the tropics right at the end of the last ice age. And that to me is a big question and something that we don't fully understand yet. Let me tell you the other thing that we have learned. And this is, again, sort of a hard figure. So let me explain it first. What I'm plotting is elevation. So this is at sea level 0, and this is high elevation over here. And then this is simply temperature at the end of that last ice age, so about 20,000 years ago, with warm temperatures up top here and colder temperatures down here. And this is the modern. So if we take temperatures based on lakes in the Ruwenzori and in East Africa, this is what it looks like. So temperature cools as you go up in altitude, and it does so at this rate of about minus 5.8 degrees C per kilometer. That's the lapse rate, the decrease in temperature with elevation. But when we plot up what we understand about temperature from this glacial period, what we actually see is that it cooled more at high altitude. And what that tells me is that this lapse rate was actually steeper during that glacial period. And this indicates that there may have been a shift towards a drier atmosphere and less water vapor in the atmosphere. So to me, this is giving us a clue that water vapor might be an important player in these glacial interglacial transitions. You know this, water vapor is a potent greenhouse gas, but one that actually is really impossible to measure. And in the prior plot that I've showed, we can measure things like carbon dioxide and methane and nitrous oxide, but we can't measure water vapor. So this is a new way where we can try to track how water vapor is changed and see how that may have played a role. So that's where we're going with this. And where my research is going is to try to, we have this one site in East Africa where we've done this, is to try to expand this more widely across the tropics to see if this pattern holds true. And then investigate the mechanisms of what could be influencing these changes in water vapor. Okay, I'm going to leave it at that. I'm happy to take questions about that at the end, but I'm going to talk for, I'll say, 5 more minutes about the Dartmouth Climate Collaborative, if that sounds okay. Okay, so in addition to being a faculty member and a scientist and doing research, I have the honor right now to be the faculty director of what we're calling the Dartmouth Climate Collaborative, which is a recent initiative at Dartmouth that aligns both operations and academics across the college to really support, connect, and grow research, teaching, and learning on climate. So this started with the new president coming in, President Sian Bailak, who's shown here. She started in 2023, and she came in, and for me, my 17 years at Dartmouth, was one of the first presidents who came in and said, I care about climate. Climate and sustainability are one of my 5 pillars of what I want to improve and where I want to grow at Dartmouth. And with that, she committed nearly $500 million in climate-related capital climate-related capital improvements, with the majority of that being our energy system at Dartmouth, which was admittedly at the end of its life and needed a change and required this investment. But along with that, she didn't just say we're going to do this change in our energy system, but she said we're also going to bring along academics and teaching and learning with this across the college so that we can really use Dartmouth as like a living laboratory and have students be trained in climate and resilience and energy transitions as well. So what does this mean? Right now, we look at the Climate Collaborative as really a connective tissue. We're providing programming and support through grants and through events and through some curricular developments really across the college. So we're trying to involve the arts and sciences and the professional schools, the different institutes, centers. And I'm hoping that if you're in the Hanover area, you'll hear more events that we're going to be hosting and sponsoring over the next few years to, I hope, into the future. So let me talk briefly about what we're doing with stewardship. And what I mean by this is our operational sustainability and resilience. So this is where Sion really came in and said, we need to change things in our energy system. Right now, we burn number 6 fuel oil to heat campus. We burn that oil to heat water and turn it into steam, and then we pump that steam across campus. The power plant is at the end of its life and needs to be replaced. So the question is how to replace it. And our tactic for doing this is with number one, the goals of having a decarbonization of our systems. So having really aspirational greenhouse gas reduction goals. So these are what Sion has committed to. So we're here. We're aiming to reduce by 50% our greenhouse gas emissions by 2030. Because of some of the changes recently federally and some of the support we had from the IRA being pulled, that's probably going to be transitioning out a few years at least. But then we're aiming to be near net zero by 2050. And the way we're going to do this is sort of fourfold. This is starting out already with reducing energy demand by upgrading buildings and building the new buildings that we have to be really energy efficient. If you've been on campus, there's a ton of construction going on campus. That's our transition from steam to hot water. Steam is incredibly inefficient in terms of transferring energy. And so all of the big digs that are going on campus are really changing the piping so that it can handle low temperature hot water to pump energy. And then going to carbon-free heat sources. One of these I'll talk about is geo-exchange. That's going to help us reduce the need of electricity to heat and cool, and then aiming for zero carbon electricity resourcing. So I mentioned geo-exchange. We're experimenting with this and hoping to learn how to do this and scale up to do this at an institutional level. The idea is that we are going to have this heating and cooling with low temperature hot water. And then in this winter, we'll be able to pump water down into the subsurface, have it equilibrate with a relatively warm temperature during the winter of the subsurface, pump that back up and have to heat it just a little bit more for heating, and then the reverse in the summer. So pumping that water down, letting it cool off relative to the summer air temperature, pumping it back up and using it for cooling. So again, we're starting this process of experimenting with this. If you want more information, there's a little QR code. You can scan that down there and find out more about it, or I can provide a website. The Climate Collaborative also has a whole academic aspect of it, which is investing in climate scholarship and teaching. And I think our main goals really are, number one for me is cultivating what I call climate leaders. So allowing students across Dartmouth to graduate, no matter what discipline they are in, no matter if they're undergrad or grad students, to graduate with expertise, knowledge in climate in their field, and then also the inspiration and sort of inspired pathways of where they can go with that knowledge and how they can make a difference in the world. We're hopefully investing more in the amazing climate research that's going on across fields. And then also we have this really amazing thing at Dartmouth where we have incredible lands here, including our campus and places like right up the road from Kendall of the organic farm. We have a second college grant land, 27,000 acres of wooded land in northern New Hampshire. And so we're really aiming to help support these and help support research on lands to have more experiential learning opportunities and to invest more in the land and to the communities. These are our identified areas of scholarly excellence that we're working in. And you can see these are sort of across disciplines. So forest and farm, climate impacts, health, wellness, and climate change, cold regions in the changing Arctic, and environmental humanities. This is our Dartmouth is Living Lab program. This is our grants program that we have up and running right now, is supporting research that involves scholarship and study and teaching and learning on lands. And there's some really fun stuff going on. So I'm excited about this and growing this. That is all I have. This is our website for the Climate Collaborative, and I'm happy also to provide, I didn't provide the link to the energy transition website, but I can send that out too as well. But let me wrap that up.